Hello students, welcome to EPG Pathshala. I am Dr. Ayushi Paliwal from Deshbandhu College, University of Delhi. Today we are going to discuss about the module Structure of Materials and Overview from the paper Functional Materials. Main points which will be covered in this module are the detailed procedure to estimate the Miller indices and direction of a plane will be discussed. Packing in closed structures like simple cubic, face-centered cubic or FCC, body-centered cubic or BCC, and hexagonal closed packed structure or HCP will be discussed. Interstices in structures have been mentioned. Structure of commonly covalent bonded materials and ionic solids will be discussed in this module. So let us start with the basic introduction. In past lectures, we have reviewed the aspects related to bonding between the atoms in a material, which determines its properties, hence its functionality, as well as laid down a basis for the structure of materials. In terms of elementary crystallography, in this final lecture regarding the structure of materials, we will now look at the method of quantitatively expressing the places and directions in the crystals, followed by the formation of closed packed structures, and then the structure of few functional common materials. Let us start with planes and directions. These are essential for the completeness of crystal structures. Miller indices, which has been named by the name of William Hallowes Miller. Crystallographic planes. First, we will identify various faces seen on the crystal. HKL for a plane or curly bracket HKL for identical set of planes where H, K and L are integers. Now we will discuss about the directions. Atomic directions in the crystal are represented by square bracket UVW for a direction, UVW for identical set of directions, where U, V, W are integers. Now let us discuss about how to determine the Miller indices. A crystallographic plane in a crystal satisfies the equation, that is H by A multiplied by X plus K by B multiplied by Y plus L by C multiplied by Z is equal to 1, where H by A, K by B and C by L are the intercepts of the planes on x, y, and z axis. A, B, and C, these are the unit cell lengths. H, K, L are the integers which are also called as the Miller indices, and the plane is represented by a small bracket h, k, l. The Miller indices of a plane are determined in a manner which we will be discussing now. Let us build a hypothetical unit cell with unit cell parameters as 4a, 8a, and 3a. The plane in consideration is the shaded plane, which intersects the a axis at 2a, b axis at 6a, and c axis at 3a. Now we take the following approach to determine its indices. First, we determine the fractional intercepts on A, B, and C axis, which are 2a divided by 4a, 6a divided by 8a, and 3a divided by 3a. Now take the reciprocal of these fractional intercepts along 3 axes as 2, 4 by 3, and 1. Now convert these fractional intercepts into smallest set of integers such as 6, 4, 3. Hence, this plane is identified as small bracket 6, 4, 3 enclosed in parenthesis. Crystal planes. A reverse approach is to be taken when one needs to draw a plane in the unit cell. So students, this approach allows one to draw a plane within a unit cell without the need to step out of it. Often, some comes across with negative indices which are dealt with by shifting the origin appropriately with respect to the axis whose indices is negative. The family of planes, that is, similar types of planes, example in a cubic system, can be represented a curly bracket HKL. As an example, take square bracket, or we can say a curly bracket 1, 1, 1 planes in a cubic unit cell which represents all of 1, 1, 1, 1, 1 minus 1, 1 minus 1, 1, minus 1, 1, 1, 1 minus 1 minus 1, minus 1, 1 minus 1, minus 1 minus 1, 1, and all minus 1s. However, one must be careful in using this convention when system changes to tetragonal, where 110 plane is not equivalent to 101 and 011. Further, the interplanar angles in a cubic unit cell are given by cos theta is equal to h1 h2 plus k1 k2 plus l1 n2 divided by h1 square, the square root of h1 square plus k1 square plus l1 square, similarly multiplied by the square root of h2 square plus k2 square plus l2 square, whereas interplanar spacing is given by d hkl is equal to root a by root of h square plus k square plus l square. These expressions are valid only for cubic unit cells. For non-cubic systems, the interplanar angles and spacings would be different. All these figures shows the various examples of the planes having a definite Miller indices. Now here the D100 denotes the spacing between the two 100 planes, whereas the D200 denotes the spacing between the 200 planes. Directions, which are denoted by square bracket U, V, W. Vector components of the directions resolved along each of the crystal axes is reduced to smallest set of integers. Crystal directions. The process of locating a direction is straightforward. The idea again is to depict the direction within a unit cell only. For example, square bracket 231 direction would be achieved by determining the intercepts on each axis by dividing the integer by the least common factor, which is 6 in the present case. So 1 by 3 intercepts on the cell of A length, that is x-axis, 1 by 2 intercept on a cell of B length, that is y-axis, and 1 by 6 intercept on a cell of C length, that is a z-axis. To find the indices of a direction, reverse approach is adopted. For negative indices, one needs to shift the origin with respect to the negative indices. Here the direction is always denoted with a square bracket and family of directions in the form of UVW enclosed in a parenthesis. Miller indices in hexagonal systems. Although a 3-digit notation is sufficient to depict places and directions in all structures, sometimes in hexagonal systems, a 4-digit notation is used. For planes HKL, it becomes HKIL with H plus K equal to -1 or -I. For directions capital UVW, it becomes small UVTW with capital U is equal to 2U plus V. A capital V is equal to 2V plus U, and this capital W becomes equal to small w. The use of such a notation enables crystallographically similar set of planes or directions in a hexagonal crystal to be denoted by same set of indices. In a hexagonal cell, 3 axes A1, A2 and A3 are coplanar in the basal plane with an angle of 120 degree between them, while 4th axis or the C-axis is perpendicular to the basal plane. The examples of planes in directions in a hexagonal unit cell are shown in the figure. Wies zone law. For a direction UVW lying in a plane HKL, H multiplied by U plus K multiplied by V plus L multiplied by W is equal to 0. This is an useful expression to determine the common directions between various planes. Packing in solids. While bonding between the atoms is a crucial factor in determining the material properties, how atoms pack in a solid, their structure, and lattice parameters are affected by factors such as processing method, form, and variables such as temperature. The graph shows the plot of energy, potential energy, versus separation distance between the atoms. As the diagram suggests that higher the separation between the atoms leads to higher potential energy, and closely packed dense structures tend to have lower potential energy and are more stable. This forms the basis for why the most materials, with the exception of glasses, tends to be crystalline with densely packed arrangement of atoms with a lattice periodicity. The glasses are non-crystalline, lacking periodic order. Since glasses have higher potential energy, they are metastable materials. Typically, if we wish to convert a material into glassy phase, we would need to suppress the formation of crystalline phase, example, by extremely rapid cooling from a molten or vapor phase. As far as normal glasses, example silicate based, are concerned, we are able to form them and use them because of sluggish kinetics of crystallization. Glasses are typically formed by addition of agents which slow down the kinetics of crystalline phase formation and lead to the retention of the structure of liquid phase itself with no long range order. Now students, let us discuss about the metallic crystals. They tend to be densely packed. They have several reasons for densely packing. First, typically only one element is present, so all atomic radii are the same. Second, metallic bonding is not directional. Third, nearest neighbor distances tends to be the small in order to lower bond energy. They have the simplest crystal structures. Now we will look at the common structures. Close packing of spheres, or we can say, students, close packed structures. In a close packed structure, the atoms are arranged in such a fashion that they maximize the number of nearest neighbors around them. For a spherical atom, by geometry, it can have a maximum of 12 neighbors, 6 in a plane and 3 each in the plane above and below. The figure shows the manner in which close packed structures can form. After the formation, the base layer, that is A, in which each atom has 6 nearest neighbors, the next layer, that is B, which is of identical configuration, can sit on either of the sides, which are marked by 1 and 2, but not both. Suppose the B layer arranges itself on A layer such that site number 2 remains exposed. Now, further, one can keep adding layers on the top. The third layer can sit on the top of the site number 2, forming a C layer, or can sit in such a fashion such that it is direction on top of A layer. Hence, there are two kinds of close packing configurations possible, that is ABC, ABC, ABC and AB, 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 both of which have similar packing density and the atoms have similar number of nearest neighbors, that is 12, but are different in the way layers are stacked as shown in another perspective. Crystallographically, ABC sequence of atoms can be described by face-centered FCC lattice, or it is also referred as cubic closed packed or CCP structure. On the other hand, AB packing is called as hexagonal closed packed structure, which is described as a hexagonal lattice. Cubic close packed structure. As evident from the figure that this ABC packing corresponds to the cubic close packed structure, or it is also referred as the face-centered cubic lattice. Face-centered cubic or FCC structure, or FCC stacking sequence. In a FCC unit cell, the ABC stacking is along 1-1-1 direction of the unit cell, whilst the plane of the layer is 1-1 plane. So we can see the 2D projection where there are A sites, B sites and C sites. As one can visualize, each atom in the unit cell has 12 neighbors called as coordination number, and the packing fraction of the structure is 0.74, which can be calculated by dividing the volume of all the atoms in a cell by total unit cell volume. The closest packed plane is 1-1-1 and the closed packed direction is square bracket 1-1-1. The below diagram shows the schematic of the FCC unit cells, where different colors are only shown just for illustration, otherwise all atoms are the same. Hexagonal close packed or HCP structure. In this structure, the AB layers are stacked along 0-0-1 or C axis of the unit cell, while plane of the layer is called as basal plane or 0-0-1 plane. The figures shows the 3D projection and the 2D projection of the HCP structure. The packing density and coordination numbers are similar to that of FCC or CCP structure. Here, 0-0-1 plane is the closed packed place with the square bracket 1-0-0 direction being the close packed direction. Hexagonal crystals. The diagram shows a simple hexagonal crystals where a plane is represented by HKIL, where H plus K plus I is equal to 0, and the direction of the plane is represented as UVTW, where U plus V plus T is equal to 0. There are various other packing methods. These are simple cubic and body-centered cubic stacking structure. Simple cubic structure. This is the rare structure due to poor packing. It has close packed directions having cube edges. In this structure, the atoms are simply arranged at the corners of a simple cubic unit cell. As a result, the structure is not closely packed and has a packing fraction of 0.52. It has a coordination number of equal to 6. Body-centered cubic structure or BCC structure. In this structure, there are 2 atoms per unit cell with 1 atom at the corners of the unit cell, whilst other is located at the body center. It is not a closed packed structure and has lower packing fraction of 0.68. As a result, each atom has 8 nearest neighbors. The material does not have a closed packed plane, but the closed packed direction is square bracket 1, 1, 1, and the closed packed directions are the cube diagonals. Interstices in the structures. In closed packed structure, although the atoms touch each other in a closest possible manner, there are vacant spaces in the structure. These vacant spaces are called as interstices or interstitial voids. In closed packed structures, there are primarily 2 types of voids. First is tetrahedral void, second is octahedral void. A tetrahedral void is basically at the center of a tetrahedron which is formed by 4 atoms. 3 of these atoms lie on the closed packed plane and the 4th, forming the apex of the tetrahedron, lies in the plane above or below as shown in the figure. As one can find out by geometry, the maximum size of an atom that can fit into a regular tetrahedral is 0.225 R, where R is the size of host atom. An octahedral void is located at the center of the octahedron, which is formed by 6 atoms, 3 of them lying on the one plane and the other 3 lying on the adjacent plane as shown in the figure. As one can easily find out, the maximum size of an atom that can fit in an octahedral void is 0.414 R. Here, the various examples of the octahedral and the tetrahedral voids have been shown. Structure of the engineering metals. Metallic crystals tend to be densely packed, although there may be several reasons for dense packing. Since only one element is present, so all atomic radii are the same. Metallic bonding is not directional. Nearest neighbor distances tend to be small in order to lower bond energy. They typically have simple crystal structures such as BCC, FCC, and HCP with relative high packing density. In these structures, one assumes an atom to be a hard sphere which are pressed against each other. Most engineering metals and their alloys follow the simple structures which are shown in the table. Structure of common covalently bonded materials. Some of the common covalently bonded materials are carbon, that is diamond and graphite, silicon carbide, zinc oxide, and a few iodides and phosphides. For example, diamond is covalently bonded with each carbon atoms having tetrahedral coordination and has a FCC structure as shown in the figure. Other covalent compounds such as silicon carbide, cubic zinc oxide also follow similar structure but with a slight modification. FCC lattice formed by one type of atom and tetrahedral voids occupied by the other atom. Other form of carbon, that is graphite, is also covalently bonded, but it has a layered structure between whom the bonding is secondary, imparting graphite excellent lubrication characteristics. Structure of common ionic solids. In the formation of ionic solids, typically ions make the base lattice due to their larger size, whilst cations occupy the interstices. Electrostatics plays a crucial role in stabilizing a particular structure. The structure formation is governed by Pauling's rules, which are essentially based on the criterion such as radius ratio, minimization of electrostatic energy, and Coulombic repulsion. The structure of a few ionically bonded materials are categorized below. Structures based on FCC packing of anions, Rocker salt structure, NaCl, MgO, FeO, MnO, etc. Fluoride structure, antifluoride structures, normal and inverse spinel structure. Structures based on HCP packing of anions, wurtzite structure, corundum, ilmenite, and lithium niobate. Perovskite structures which are cubic or non-cubic. And there are mixed perovskites also. Now let us discuss about the alloys. Most materials consist of some second element, usually to obtain improvement in the properties. For example, steel is nothing but the iron carbon alloy having less than 2 weight percentage carbon. Brass, take for an example, is a copper zinc alloy which is having up to 50 weight percent of zinc. The last example is bronze, which is copper tin alloy having up to 12 weight percentage of tin. So students, let us summarize what we have learned from this module. First, we discussed about the planes and directions and the different ways to quantify the facets and the directions of unit cells, which are very useful in representing a directional dependence of properties. Second, metallic crystals, which are typically crystalline in simple structures like simple cubic, body-centered cubic, face-centered cubic, and lastly, hexagonal closed packing. Third, interstices in them play an important in determining their properties. These we have discussed in the detail. Thank you.